Okay, so we're going to graph y equals x cubed minus 1 over x cubed plus 1. This is section 4.5 of Stewart Calculus, number 18, curve graphing. And I think we can all quickly see the domain of this is all real since it's a rational function. At negative 1, it is undefined. Also, by plugging in 0, we can also quickly see that the y-intercept is 0, negative 1. Two quick things. I also then think to myself, the limit as x goes to infinity gives me a horizontal asymptote of 1, and that's here in blue on the right. Okay, so now I know the horizontal asymptote. Now, the first derivative of this function, I'm not going to spend a lot of time with this, all right? In red here, you'll see that I have 3x squared times the quantity x cubed plus 1. Derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. F prime g minus g prime f over g squared. Now, we do need to do some simplifying, which I did in green. All right? I distributed, combined like terms, and I ended up with 6x squared over x cubed plus 1 over 2. That is the derivative, first derivative that I am going to use to take the second. All right? And again, the derivatives are just transportation. All right? And if you have to slow this down and do the work, I recommend you do it. Once you take the first derivative of that rational function again, which has a chain rule from the bottom, what I want you to notice is that each term has an x cubed plus 1 in it. So I can cancel out 1x cubed plus 1. All right? So I'm going to do that cancellation immediately. I'm going to cancel out this one, that one, and one of these to 3. And then I can distribute the 12x to the x cubed plus 1, and I can do that, and then I get this right here. All right? And that simplifies to here, and that simplifies to here. All right? It is algebra. It's a high-level algebra, but it's algebra. And now I can make a big jump. I can look at these two and say, I can find the critical points of the first derivative, and I can find points of interest, possible points of inflection for the second. So where's the first derivative, 0 or undefined? Well, it is 0 at 0, obviously, for the numerator, and negative 1 makes the bottom 0, but that is not in the domain, so the critical point is just 0. Likewise, over here, I can say, what makes negative 12x 0? Well, 0. And what makes 2x cubed minus 1 0? Well, the cube root of 1/2 makes it 0. All right. I now have all the stuff I need to do my sine table. I have the vertical asymptote of negative 1, critical point of 0, and the cube root of 1/2, which in my calculator is about 0.79. And I've set up this table. All right? Negative 1's undefined. I have the first, second, and third derivative for columns. I know that 0 is a y-intercept of negative 1. I also know it was 0 for these two. So I am thinking that most likely it doesn't have a max or min. I also know that the cube root of 2 is a 0 for the second derivative. All right. So now I'm going to start doing my sine table. And on the right side, I find that it's increasing here. And between negative 1 and 0, it's increasing. And then I'm finding out to the left, to the right of 0, it is increasing. Because, guys, this function is 6x squared over junk squared, squared, squared. Negative, negative is a positive, 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 positive. I didn't have to plug stuff in. Now, likewise, on the next equation, the second derivative, I'm going to have to really work out what's going on here. I'm going to plug a negative 1 million in for left of negative 1. And I'm going to get a positive, negative, negative. Two negatives make a positive. This is a concave up curve. All right. In between negative 1 and 0, so negative 1/2. Negative 1/2 is what I think of. I get a positive, I'm going to get a negative, and I'm going to get a negative. Two negatives make a positive. All right, I'm cruising. Now what's happening between 0 and 0.79? What's happening between 0 and 0.79, if I put 1/2 in, is I'm going to get a negative 6. 1/2 is going to be a negative there, two negatives, and it's going to be a positive, so I think two negatives make a positive. And finally, if if I plug in a really big positive, I think what you're going to see is that it becomes a negative. Now, I have developed a table where there are no max or mins. I see it is always concave up except from this 0.79 to infinity, and it's not concave up or down at 0. So I think now I can go to a dual page, and I can make the graph. All right, so I'm going to graph this function then, make a big old x, y, a vertical asymptote at -1, a horizontal asymptote at +1. All right, I know it goes through the point -1, 0, or 0, -1, I'm sorry. And I know now that it's increasing and concave up to the left of -1, so it looks like this. And I know it's increasing through here, concave up, concave down. All right. So again, it works out pretty well for us. Oh, wait a minute. I made one mistake here on my sine table. That's supposed to be negative. I did it again. I said it wrong, or said it right and wrote it wrong. So it's concave up to the left, concave down from -1 to 0, concave up from 0 to 1, and concave down from 1 to 0. So we have 2 points of inflection. They happen at the intercepts, which are kind of unique. And there are no local max or mins. And we have just graphed the function.